Okay, now we continue with the second topic, which is scaling laws and miniaturization. I keep telling you on the different scale just now in the first course. I mean the first lecture about the things that does not follow the Newtonian law, Newtonian mechanics, because when you go to different scale, it behaves differently, and that is where for MEMS design you have to be careful. You have to have a different kind of intuition. Normally, if we design something at a big scale, if we used to be uh, design something at macro scale, then somehow we have the intuition that this kind of things is sufficient. Then we start do the calculation with the size of the intended design, or the things you see that okay, this will work at this kind with this kind of design. But if you work with a different scale at the micro scale, it behaves differently. So this behavior of materials and mechanics at different scale, what we call as the scaling laws. So the scale will change the behavior and the how things work at different scale. It will go, let's say you when you start at 100 micron, so it's behave differently from the macro scale. So it goes up to a few nano, for example, then you have different behavior as well. So that is where we look into different properties at different scale of the materials and also the design or the geometry itself. So that is roughly about scaling laws in the miniaturization. So it's a very well-known fact that when size diminish to extremely small levels, Newtonian mechanics fails. So in such situation, one has to use quantum mechanics for studying physical system of such extremely small dimension. So this is what I've mentioned before. However, it is less readily recognized that even before reaching such extremely small dimensions, leading to the breakdown of Newtonian mechanics, there are many special aspects one needs to take care of for successful analysis and design of small system. So even before it's failed, I mean, at the micro scale, you can see if you use a normal simulation, for example, you will get not accurate prediction. And when you kind of fabricate the device and you test, it won't be the same as if you use different software which is not accurate. For example, it won't be the same as well. And the counterintuitive features arise not due to breakdown of Newtonian mechanics, but due to the changes in the order of predominance of physical phenomena. So it's before the breakdown of Newtonian mechanics, some predominance property of the materials also change at the small scale before Newtonian breakdown, caused by a drastic reduction in size from the scale we are familiar with in our daily experience. So that is where we need to be careful and aware of the difference and the change of the property at different scale. For example, in simple language, this is called scaling effect. And the laws which govern such effect are called scaling laws. While dealing with a microsystem, our normal engineering intuition fails and it needs to be replaced by special micro-intuition, we call it, for developing microsystem, which is becoming a very important engineering activity with the turn of the century. So let's say you have at macro scale, you have phenomena A and B predominance in this kind of scale, and then it change what is the predominance phenomena in different scale. Let's say this is a micro, let's say this is nano, so it's changed according to a certain level of scale, certain level of geometry, size. So at, let's say, between range of 500 to 800 micrometer, so it behaves differently. But now, I mean, the predominance phenomena different, but then you go up to nano, then different phenomena will happen to the properties of the material, of the behavior of the material at different scale. One would intuitively simple scale down the size of all components to the device to make it small. Unfortunately, the reality does not work out the way. So if you simply think that you make things small, then it will work as intended when you have at the macro scale. It's not the case. So it will behave differently. So there are serious physical consequences of scaling down many physical quantities. The scaling laws will make engineers aware of both positive and negative physical consequences of scaling down machines and devices. So we will look into this content, which is about scaling the geometry, how it works, and what will happen. Then we look into the rigid body dynamics, and then scaling in terms of electronic forces. When you scale down, you make things small. What happened to your electrostatic forces, electromagnetic forces, electricity, fluid mechanics, and heat transfer. So miniaturizing machines and physical system is an ongoing effort. As I mentioned before, we try to reduce consumption of materials. We try to make things become more sustainable and increase the performance, etc. And this effort has been intensified in recent years as market demand. And you have your intelligent, robust, and multifunctional, and low cost. So these are the things that we want to achieve. We want to have intelligent things. We want to make things lighter. You want to have your handphone lightweight, your computer lightweight for mobility. But we have to aware. But at a certain extent, we want to have the things to become cheap, right? We want to have high performance, but we want to have it at low price, right? Then if we make it smaller, we can reduce the materials, and we can use less material than with the intention of it become cheaper, because we use less material. But the thing is, the process itself consume a lot of energy and difficulty. So that's why even though you make the circuit at 2 nano with less material, but now the 2 nano is an expensive process. It's difficult. So at the end of the day, you will still pay quite a lot of money for the performance, right? And a consumer product has become more strong than ever. The only solution to produce this consumer product is to package many components into the product, making it necessary to miniaturize each individual components. So if you can see that your camera, yeah, the camera of your handphone. So now the performance of the camera become very high performance and a good quality of photo, right? You can capture. So you cannot imagine you can have a photo of taken by your phone camera at the quality of digital single lens DSLR camera. So now you can have 12 gig or 24 gig of memory as well at your phone. Previously is almost impossible. So that is where miniaturization is heading to. And miniaturization of miniaturization of physical system is a lot more than just scaling down the device component in size. Some physical system either cannot be scaled down favorably or cannot be scaled down at all. So we have to acknowledge that some things that we cannot scale down as well. It's not that everything can be scaled down to make it small. Okay, and scaling of geometry basically is about scaling of physical size of object. So it has effect on the mechanics of the things as well. And scaling of phenological behavior, scaling of both size and material characteristic or characterization. So when you scale down the size, you look into a different behavior in terms of the material properties. So what happened when you scale down or you change the size from big to small? So basically, you change the volume, you change the surface area, are two physical parameters that are frequently involved in machine design. So we know that volume is cubic, right? I mean, and the surface is square. Okay, so that relationship basically will determine the ratio of the material and its behavior. So volume leads to the mass and weight of the device component. So you increase one dimension, basically you not just increase the weight at one dimension, but you are increasing the weight at three-dimensional because it's cubic, right? Volume relates to both mechanical and thermal inertia. Thermal inertia is a measure of on how fast we can heat or cool a solid. It is important parameters in the design of a thermally actuated device. So if you have some device, you design something that you want to actuate or to make things move using heat, then you have to consider that because of the volume, so it will be different. Volume of the device itself. How heat transfer will change if it's a big, and how is heat transfer will change if it's small. Okay. And surface is related to pressure and the buoyant forces in fluid mechanics. For instance, surface pumping by using piezoelectric means is a practical way of driving fluids flow in capillary conduits. When the physical quantity is to be miniaturized, the design engineer must weigh the magnitudes of the possible consequences from the reduction on both the volume and the surface of the particular device. So it's all about volume and surface ratio, basically, if you look into the device at the micro scale, the behavior. So yeah, if you let L in the linear dimension of a solid, we will have the volume is proportionate to I3. So I is not L, I here. So I3. So the surface is proportional to I2 square, and this is cubic. So the ratio of S and V is L to the power of -1, right? 3 and 2. So a 10 times reduction in length will cause 1,000 times reduction in volume. Okay, so that is the consequences of changing the dimension. Just one dimension, you will change the volume 1,000 times. But for the surface, 100 times reduction, right? So in the surface area. So that is, we'll conclude this since volume, V relates to mass and the surface area, S relates to buoyancy force. So we see that comparison elephant and dragonfly is how difficult for elephant to fly in comparison with a dragonfly. Okay, so an elephant can never fly as easy as a dragonfly. So because of this volume, the mass of the elephant of the different dimension in comparison with, in relation to the buoyancy of the shape or the geometry. So what would happen to the required torque to turn a micromirror with a 50% reduction of size? So micromirror is one of the quite common design or device in MEMS. Micromirror is basically a mirror that you are using for scanning. So you rotate or you twist the mirror in order for you to reflect some light to do the scanning of things. So let's say you have your device to scan something, so you use micro mirror. So this micro mirror, if you make it smaller, then how, let's say you reduce 50% of the size, then torque required to turn the micro mirror is this equation, where Iyy is the mass moment of inertia of the mirror about y-axis, is with the following expression. So in which m is the mass of the mirror and c is the width of the micro mirror. Then further calculate, then you get this, with this rho as the mass density of the micro mirror material, a fixed value. Thus, we have this equation. Then a 50% reduction in size would result in the calculate all these things, you solve for this equation, then you get the factor of 32 times reduction in required torque. So it's not 50% reduction in size, 32 times 32 times a reduction in required torque. Okay, that is a quite, a lot of the reduction in required torque. It's not just double, because if you see that this is 50% is a kind of half of the size, right? So you might think if it's half of the size, you might reduce half of the required torque. But actually, you reduce 32 times of the required torque. So that is where, because of the density and the mass of this is, change. As we looked before, the change in one dimension will change 1,000 times of the mass. And forces are required to make parts to move, such as in case of micro actuator. So micro actuator like piezoelectric or electrostatic, power is the source of the generation of force. An engineer needs to resolve the following issues when dealing with the design of a dynamic system, such as actuator: the required amount of force to move a part. So I think I've shown this. I've shown this in the previous slide, where we try to calculate the force or try to predict the force that can be exerted by a certain actuator, or in particular piezoelectric actuator, and we have to calculate or predict the required force to overcome certain stiffness or the spring stiffness. So how fast the desired movement can be achieved. So this might be the frequency or the resonance of the system, and how readily a moving part can be stopped. And so this will change when you have a different mass. Okay, for example, how fast you can achieve it, if it's become smaller, then it will become higher frequency is possible, rather than at the micro scale that you need a more torque. The resolution to the above issue is the inertia of the actuating part. So the inertia of solid is related to its mass, and the acceleration that is required to initiate or stop the motion of a solid device component. In the case of miniaturizing this component, one needs to understand the effect of reduction in size on the power, force or pressure, and time required to deliver the motion. So these are all the scaling law that needs to be looked or calculated prior to the design of the materials or the device. So rigid body dynamics is applied in the design of micro actuation and micro sensors. And it is important to know how size, as mentioned, affect the required forces and thus power in the performance of this device. So we are familiar with this equation, F equal ma. A is acceleration. So this is the normal rigid body in motion. Acceleration can be computed from Newton. And the accelerating in the Newton law can be expressed in the following way in the scaling. So let the displacement of the rigid body as proportional to L, in which L is the linear scale, but velocity v equal s divided by t. and hence V proportional to LT to the power of -1, in which T is the required time. Okay. For particle kinematics, the equation is S equal V naught times T plus half of AT square. Then these are all the equations related to the rigid body dynamics. Then you can get your F equal ma initially. Then you replace with all these. Then you get this equation. So it's with this you can try to look into your scaling of the vector in terms of how much force can be exerted, then how acceleration will happen, then time required, then the power density of the systems. So which in the order of the acceleration, you can see that if you have scaled the force, I mean, if you with the order of 1, I mean the size order, then the force equal, then the acceleration reduced to -2, meaning -2 times. Okay, and the time is 1.5 times, and the power density minus to 2.5 times. Time is I mean, you get better. So in which order means the index alpha is the scaling of a quantity in the linear dimension. For example, weight proportional to V, then pressure proportional to 1 over A, then for the order of positive and negative sign, order of decay proportional or reverse proportional in scaling. So this is the reverse with minus, and this is a positive. So the power density, when scaling down a MEMS or microsystem, one must make sure that the power used to drive the device or system is properly scaled down to. In the design practice, power density rather than power is used, and power is defined as energy. So produced or spent by the device per unit time, and the energy is related to work. So here, the relationship can be expressed as this. Okay, I think everyone know P is power, force, etc. And for example, estimate the associated change in the acceleration and the time and the power supply to actuate a MEMS component if its weight is reduced by a factor of 10. So if we reduce the size by 10, then the weight by time, not the size, the weight by time, 10 times, then what will be the acceleration, etc. So you see here, this relationship that we have established before. So it's involved scaling of 3, the order scaling of 3 from the table. Then there will be no reduction in the acceleration. Okay, and there will be 0.5 increase in terms of 0.5 times here, and to the power 10 to the power, yes, because this is 10 times weight. Okay, and 3.16 reduction in the time to the complete motion, because 1.5. There will be 3.16 times reduction in the power density. The reduction of power consumption is 3.16 of V naught. Since the volume of the component is reduced by a factor of 10, the power consumption after scaling down reduced by P of 0.3 times. So meaning to say, if you reduce the weight of certain components in MEMS, you can reduce the power required by 0.3 times. Okay. So electrostatic force. So as I mentioned before, you have electrostatic force for the actuator. So electrostatic force or electrostatic com drive normally being used quite common in MEMS because it's easier and it's provide quite significant power to have an actuator. So the concept is very simple. When two parallel electric conductive plates is charged by a voltage, you have electric potential between these. So the corresponding potential energy is this. So the linear scale of the electrode that we have is this, and then you can get the scaling of the voltage. V can be approximated by the Paschen effect. So if you have, this is at 5 micron size, this is 10 micron, then you can get your gap. This is the gap. Then this is the size reduced. Okay, the breakdown voltage will be higher if the scale is decreased in comparison with this side. So we will use a linear scaling for the voltage here, from which we get the scaling of the potential energy. So here, a 10 times reduction of linear size of the electrode will cause 1,000 times reduction in the potential energy of the system. So, and further calculation, so you can get the 10 times reduction in electrode linear dimension, then you can get 100 times reduction in the magnitude of the electrostatic force. So just reduce 10 times of the electrode size, then you get 100 times reduction in the magnitude of electrostatic force. So that is where you can play around from the design. When you scale down or you can try to increase the size, then you can get different force, not linear. Okay, it's unlinear kind of a relationship. Then we look into electromagnetic forces. Electromagnetic forces are the principal actuation force in microscale or traditional motors and actuator. So basically, if we have this current flow in the wire, in a wire, conducting wire, then you have a magnetic field. So you can have a force on this wire due to EMF or electromagnetic force. So electromagnetic force, F is generated when a conducting wire with a passing electric current I subjected to an EMF is exposed to a magnetic field. So B. So electric magnetic field, then you can have the EMF, a flux D phi as illustrated. So basically, what the above scaling means that reducing the wire length by half would result in the reduction of a force by 2 to the power of 4, which is 16 times. So you reduce the length half, then you get 16 times forces, where the reduction of electrostatic force will similar reduction of size will result in the factor of 2 to the power of 2, which is 4 times. So electrostatic force only reduced 4 times, but the EMF force reduced by 16 times. So that is the difference in terms of scaling here. So this is the reason why electromagnetic forces are not commonly used in MEMS and microsystem as preferred actuation. So because when we reduce the size, it's become too low and is not that applicable in terms of making the actuation happen. So it's the same thing with electricity, in which rho, L, and A are respective electric resistivity of the material, the length, and the cross-sectional area of the conductor. So basically, if you reduce, is proportional to the power of -1, the resistivity. So resistive power to the power of 1, the same. So this is reduced, this is the same, remain. And in electric field, is reduced by 2 times. Okay. Then permittivity is the permittivity of dielectric is reduced by 10 times, and ratio of power loss available reduced by 100 times. So that is the scaling of electricity if we scale down the dimension. So this is just to provide you a table for a quick kind of calculation. So if you reduce the size by 1 times, so you increase the current by 2 times, basically by 100 times. Because the power of 2 here. So voltage the same. Okay. and the rest. So, and scaling laws in fluid mechanics. The fluid mechanics also, if we reduce the size, then it behaves differently. So the important quantities in fluid mechanics in flows of in capillary conduits. So you have this inner dimension. If you reduce, so the volume flow basically leads to the reduction of 10 in the conduit radius, then you have 10,000 times reduction of volumetric flow. So this is a very significant reduction if you just reduce this radius by 10 times, then you get the volume flow reduction of 10,000 times. So it's not just if you reduce the radius by 10 times, you get 10 times flow of the volume reduced, but it's 10,000 times. Okay, and another thing is on the pressure drops. So see here, if you reduce this, a reduction of 10 times in conduit radius, then you reduce 1,000 times increase. You increase basically the pressure drop per unit length. So the pressure increase 1,000 times. And for the heat conduction, how conductive the solid becomes when it's scaling down. This issue related to thermal conductivity of solid. So kappa equal this equation. So you know that at the end is equal to 1. So how fast that heat can be conducted in solid, this issue related to Fourier number defined as this equation. So this is basically 2 times. So a 10 times reduction in size will lead to 100 times reduction in time to heat the solid. So 10 times size smaller, then you get faster in heating the solid. You can get a quick heating of the systems. So that's why you can have a quick the thermal actuator, the inject. If you use thermal materials to heat up the materials very fast, so they can get fast response of the material. Okay, and scaling in micro mechanism. So we have different mechanism. For example, here, and this is hinge. Hinge, as I showed you before, the size of the hinge, for example, and the shape of this hinge in the design of the previously shown micro stage before. So this kind of design also will have a different scaling laws in terms of the geometry and the mechanics. So you have different shape in this shape and in this half revolute shape and this spherical shape, etc. Then you will have the different scaling. Okay, for example here. So if we refer to number 1 here, you can see the scaling effect is L to the power of 1, which is the same. So if you look at this here, 2 prismatic. Here, right, the prismatic. So it's 2 times, right? Meaning if you have 10 times reduction of the size, you have 100 times of the reduction of the stiffness. This is increase, not reduction, okay? Because it's not minus, it's a power of 2. So the deflection characteristic Dmax of these commonly used fractural hinges is seen from the expression of the Dmax that except for the first and fourth cases, Dmax is independent of the size, but in the first and the fourth cases, these fractural hinges tend to behave much stiffer at the small scale. So for the design of the micro scale, so we can see that different uh, properties, different scaling, you have some scale of the reduction reduce or increase 1000 times of the behavior, and some properties doesn't change, but some properties or the performance reduce, for example. So it varies. So it depends on the phenomena that we look before. So here it's not just about uh, reduction of certain behavior, but here at certain size, it will have different phenomena that predominate the property. So if certain property predominate at certain size, so it will change the behavior. So it's not everything change, but sometimes you have the power of 0, which does not change at all, but the power of 1 change of 10 times, for example, power of 2 change of 100 times. Okay, it depends on the, uh, well, it go back to the equation of the uh, Newtonian mechanics, Newtonian law, but somehow because of the ratio of the properties is different between volume and size and in the surface area, so then you can have different kind of phenomena that happen. So that is about size related to volume and surface area, but of course the different properties in terms of uh, let's say the fluid flow, etc., you have to look into the properties, I mean the equation of the fluid mechanics. And for the heat transfer, you have to look at the equation of heat transfer. But everything, as I said, refer back to the fundamental of the size as well. So the volume and the surface ratio, then you integrate into your fluid mechanics or heat transfer equation. So then you can get the relationship between the reduction of size, reduction of one dominant linear length, for example, in terms of looking into the properties of how fast you can heat up certain things and how fast you can move certain things. I mean, the frequency and the resonance of the things. So in order to avoid disaster in designing the device. Let's say you design the device quite, uh, of course, if you want to talk about mass, you have to look into the density of the material as well. So different material has different density. So with different density, you can get, I mean, different mass, you can get different resonant frequency of the things. So resonance is quite important in designing MEMS devices because you want to prevent from damage. Okay, and resonance because you want to actuate something, to move something, let's say the micro mirror or the cantilever or the motor. So that is where you need to look into materials before it achieve the or the size and the actuation that won't go into the resonance. Okay, so that is where you need to be careful and design from the beginning with regard with the intention in mind of the scaling factor that will happen to the materials and the device itself. Okay. Okay, I forgot that I have this in this slide as well. Okay, so basically, if you look previously, I mean at these hinge flexures, so here is the hinge that I've been talking about. Okay, so with this kind of different type of hinge, basically it will provide different stiffness as well. So these are the hints that can be used. For example, but the scaling effect is here. Oh, sorry. The scaling effect is here. So you can have a simulation of this kind of hinge, then get the power output. Okay, but the thing is, the next things that we have to think is the materials. Let's say now we are talking about, I've been talking about 2 nano. I mean, previously 3 nano line size. So it's not just about a difficulty in terms of fabrication process. So, but we need to think of when it goes to 2 nano, so what will happen to the resistivity of the materials? Right, you apply current and voltage to the line to transfer the electricity, I mean to the signal. So we know that the heating will be quite fast, but the heat transfer will be fast as well, right? So that is the good thing. But the fast heating might have some effect. But of course, this need to be investigated. And of course, they have done it before they want to produce mass production for this kind. But what I'm trying to say is the behavior at this 2 nano, this is nano level, might be almost the same thing, maybe slightly different with nano. But previously, we have a micrometer size. So definitely the micrometer size will be very much different at the nano scaling size. So you see that the relationship here for the electrical, right? The current, power of 2 here, and the voltage 1, the capacitance, etc. This will have an effect to the device itself. So the retention of the the capacitance. Okay, that's all. Any question? Is it too early? Anyone has done something about micro scale devices? You have studied, no micro device at all?
Professor, nice presentation. So I have a small query. When you increase the pressure, then definitely it will affect the thermoelectric property. You have discuss about conductivity. So if you increase the pressure on the materials, so the band gap will be more closer, means that will be more small. External pressure.
Increase the pressure.
Then the band gap will reduce, correct? In a material, if you apply external pressure,
you mean at the constant level of external pressure, you can reduce band gap?
Band gap of the material.
Okay.
If you reduce the band gap, it will affect the all other properties like thermoelectric property or optical property, correct?
Maybe. I'm not sure. Okay. But the thing is, that is the situation where you provide constant pressure to the system, to the materials itself. Normally, when we design the materials, for example, is whatever the process we done at the, let's say we increase the pressure to do something, but in normal operational condition is at the atmospheric condition, right?
Like suppose you will design a pressure sensor.
Yeah.
using MEMS, pressure sensor.
Yeah.
So in that case, you have to apply external pressure.
No, pressure sensor works when you have pressure and you detect pressure.
Yes.
Yes.
You have to apply external pressure.
Yeah, kind of applying external
Yes.
pressure. Yeah.
So if you apply that, then obviously the voltage and current output will change.
Voltage and current output will change.
Because that is the process in which you can detect the output.
The current, well, it depends on the materials, right?
Yes.
Yeah.
Yes. Okay.
So let's say, I mean, we are talking about piezoelectric, for example, right?
Yes.
Piezoelectric itself will induce electricity when you apply strain,
Yes.
right?
Yes.
So the strain applied to the material will induce electricity, but different materials, let's say let's say you mentioned about thermoelectric, right? Thermoelectric itself is will induce electricity if you apply thermoelectric heat, because it's
Yes.
respond to heat, right?
Yes.
Yeah. So in a way, it won't respond to the pressure. Yeah.
No. Okay. Okay. Thank you.
Yeah.
Thank you.
That's what I understand. I'm
Yes,
not
yes.
sure.
Yes. 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 Obviously.
Are we too early?
We have another 5 to 10 minutes.
Okay.
We can discuss.
Yeah, sure.
Okay. I'm audible, correct?
Yeah.
No, but in recording it will not. You discuss about scaling of resistance, resistivity,
Yes.
capacitance.
Materials, yeah.
Can you tell some technique to scale, because it is a MEMS nanoscale device, so you need a minimum voltage, minimum current to operate these devices.
Yes.
So is there any procedure to scale down the voltage as well as current in the device? Because the voltage should be as low as possible, the requirement input voltage. So is there any procedure to scale down those voltage and current?
To scale down the voltage and currents in terms of the required voltage and current for the operation, right?
Yes, input voltage. Input voltage.
Input voltage. So it depends on what is required for the device to do. So if the device needs high force, let's say you need to apply a certain extent of voltage to make sure that the force can be exerted to do the work. I mean, if you're talking about, let's say, electrostatic forces need for the COM drive, so at a certain extent, you scale down the size, then it will reduce the force. But you want to maintain a certain force so that when you design the device, you have a certain extent of robustness. Robust meaning it won't easily break when the stability. Okay, so that is the trade-off between the required electrical power, the required current and voltage in order for you to apply to the system so that it can work. So of course we want to have a low power so that you can have a more efficient devices. I mean, that is always the case, but well, that will be the design that required in terms of the specification itself. So if the spec required, let's say, movement of certain level or the force at certain level, then we have to cater for that requirement instead of, I mean, maybe optimization of the input current will be kind of different aspect. I mean, another study, but for the requirement of the device itself, need to be fulfilled at certain extent. Yeah, that's what I can say. Yeah.
Actually, I am not from mechanical engineering, so I belongs to electronics.
Okay.
So I understand what is the readout in your circuit. Means what are the parameter in the output side? You will tell yes, this device is working fine.
It depends on the size again.
No, I am talking about the parameter in the output side, whether it is force or
nano. It can be nanonewton, or it can be micronewton.
means force. It is
Yes, yes.
okay.
So if it's about a movement, it can be nano, it can be micro scale of movement.
Okay.
So that is depend. That's why I said it's depend on the design and the requirement of the device itself. What you want to do with the
So
device.
what is the application of this device?
It depends. Let's say if you talk about micromirror, it's about doing the scanning.
Yes.
If it's about cantilever, you want to detect some heat or some biological materials properties.
Means you are talking about sensor.
Yes.
It's
Yeah,
something
yeah.
like some disease can be detected
Yes.
with these micro sensors.
Yes, that's true. Or we can make a MEMS speaker, right? The speaker by MEMS devices. So the extension of movement is depends on the design of the speaker itself.
So a diaphragm can be designed with MEMS.
Yes,
correct?
Yes, that's true.
Okay. Thank you
Yeah.
so much.
A very good question from different background of people. Biomems is actually quite interesting and emerging field. Biomems refer to MEMS devices for bio application. So normally it will be related to healthcare and medical kind of instrumentation. So that also, I mean, it's a MEMS, but people try to coin it as biomems in order to differentiate the application. So MEMS device in biological and medical devices will be called biomems. But for electrical application, such as RF radio frequency, we don't call it, let's say, electric MEMS.
We also work on MEMS in our department.
Okay.
So most of the participants they are from undergraduate branch,
Okay.
mechanical engineering. So in your university or in Malaysia, in government of Malaysia, is there any kind of scheme during summer? We have 2 months summer for every year. So during summer they can visit different university with a scholarship for faculty as well as student. Is there any scheme like that?
We don't have any specific scheme, but it's upon request we can arrange.
So they will be getting stipend during that period.
We don't have that kind of, I mean, specific scheme to provide stipend and everything. We, in fact, I mean, I'm sorry to I mean, maybe mention this. Normally, we kind of the arrangement will need the participant to pay instead of getting stipend. They have to pay kind of, we call it bench fee. So the bench fee will be required unless the institution have MOA in advance, then it will be waived.
In our ministry in science and technology, we have a scheme for all Asian countries like Malaysia, Vietnam. Every year, the students from those universities can visit India, different universities to have research. What is the current research ongoing in India?
Okay.
They can visit with fellowship.
I see. Yeah, I know. The postdoc, right?
Yes.
Yeah.
It is for 2 months, not exactly postdoc.
Okay. Yeah.
It is for 2 months. For undergraduate student, it is particularly the focus.
I see.
So they will be getting a stipend. So maybe in your ministry, science and technology.
So far, no. As far as I know, as far as I know, we provide scholarship. What is called a Malaysian International Scholarship (MIS), but that is for postgraduate studies. Yeah, that's all. So I mean, there are a few countries. I mean, including Indian national, can apply for that.
So
Yeah.
for postgraduate study means
Yeah.
after graduation they will be applying.
Yes, they can apply for masters or PhD. Yeah.
So during that period, what is the fellowship they will be getting?
They will get a scholarship of, I mean, it's depend on the level. Maybe the master's level is up to 2,300 ringgit, and for PhD 2,800 ringgit. So not much different, but yeah, you can survive with that.
Malaysia is cheaper compared to India. It's cheaper.
Malaysia is more expensive compared to India. Yeah. But especially in Kuala Lumpur, it's more expensive. So yeah, you can survive, but yeah, it will be a little bit hard. Yeah. But if it's different part of Malaysia, it might be sufficient. Any other question?
So thank you. It's a nice presentation, sir, and very interactive session. And sir is from electronics background, and he is also working in this area.
Okay.
So he had special interest to come
Okay.
to this session. He will be attending more sessions also. So thank you. We'll be again attending post launch session, the tutorial. So thank you.
Too early, right?